Hi, I'm Alexander McLaren, and in this video we're going to look at how to use Abaqus CAE 2020 to examine stresses in a pair of meshing involute cams. So just before we get started, this is what we're aiming for, and we're going to generate a model like this in Abaqus in two different ways. Firstly, we'll do it manually, so we'll do each step in the Abaqus user interface to create this model, just so you get to know it. And then we'll look at using a Python script to create this automatically and do the data extraction as well, such that you can focus on what you really need to in this task, which is to examine the effect on the stresses of varying several geometrical parameters by means of a parameter study. So we'll just get started. When we open Abaqus, this start session window comes up, which we can close. And then if we right click on parts and press create, we can then create a part called shaft. This part will be two-dimensional, planar, analytical rigid, and wire is fine. Now this part is literally an infinitely thin arc, which is the surface used to apply the torque to the cam. So it's good practice just to start by putting a point at the origin and then constraining that point by pressing fixed and then selecting the point and pressing done. We can now close the constraints menu. What we'll do now is long press the construction line dialog, and then we will use create construction circle, and we'll create a construction circle of radius 20 millimeters. We can then dimension this by pressing the dimensions button, clicking on the circle and pressing enter. Now what we're going to do is to create two construction lines, so long pressing again and then selecting create construction line at angle. We will select the angle, and I'm going to go for 70 degrees to the horizontal, and then we can position that. We can then press back to choose a different angle, and I'm going to type -70, press enter and put one there too. Now you'll see that while the circle is green because it's fully constrained, the oblique lines are yellow because they're not fully constrained. And so what we can do is actually fully constrain that by creating a vertical construction line and then dimensioning between the two lines, which we expect to be 40 degrees. We'll press enter, and between those two lines, which we expect to be 20, and we can press enter on that as well. So now that their angle is constrained, those lines have both gone green. Finally, we'll just create the section that actually is the part itself. So we'll have an arc, center, and both ends, and then we'll click on the origin and then define the two endpoints of the arc. That's all the shaft is, literally just one single arc. So we can press done on that, and finally we'll create a reference point. So if we zoom out, go to Tools, press Reference Point, and select the center point of that arc, we get a little RP, which stands for reference point. That is the shaft part complete. The next part we'll create is the web. So we will call this web, and this time we'll go 2D planar, deformable, and shell is fine. We're going to do exactly the same thing, so it's good practice to put a fixed point in the middle, and we'll fix that point there. And then we will create a construction circle. This is going to have the same diameter as the shaft, so radius 20 millimeters. But we'll create another construction circle as well, so selecting the center again and with radius 25 millimeters. These are the inner and outer diameters of the web, and we'll just dimension these so they don't go anywhere. The reason I'm rigorously constraining and dimensioning is because if you change any of these dimensions and something isn't constrained, in SolidWorks often the sketcher is quite good at knowing what you actually want to change, but in Abaqus things can just go completely mental, so it's good to lock things down as soon as you can. I am going to create another oblique construction line, but this time at 75 degrees to the horizontal, and pressing the back arrow again to change the angle at -75 degrees to the horizontal. I will create a vertical construction line as well, which will allow me to lock the position of these two down. And I'm going to do exactly the same procedure as before, just defining these angles. Finally, I will draw the non-construction lines that actually create the web itself. So arc, center, and endpoints, and the inner diameter, and then arc, center, and endpoints on the outer diameter. And finally, pressing escape so we don't have any more arcs, I'm going to create a line there, and then pressing escape again, and pressing the line button, another line here. Pressing escape once more, and because all of these components are fully constrained, the whole thing has gone green. Now we'll press done. And that concludes the web part. Finally, we will create the rim component, which we will call tooth, because it is only one tooth. This is the most complex of the components. We will start again with a fixed point, and then we will draw construction circles for the inner diameter of the tooth part and the dedendum diameter. So a construction circle is long click on the construction geometry button, radius 25 mil, and the dedendum diameter is 30 mil. 60 mil, radius 30. Then we will dimension these because we can, and we will create a construction line that is oblique again at 75 to the horizontal, and once more at negative 75 to the horizontal. Fab. We will also create our vertical construction line, and we will dimension such that that stays where we put it. Let's try that again. Pressing enter to get the dimensions to happen each time. We will now start creating this part. So the first thing we're going to do is just put a little radial line there, and we will put arc, center and endpoints on the inner diameter. Now I'm going to enter the coordinates of the involute itself. So this creates the tooth flank, if you like, of the cam. What I'm going to do is press the spline button. It's very important that you don't use create lines, and instead you use create spline. This is because the spline will create a curvilinear interpolation between your points, whereas the line will create a linear interpolation and create discrete lines, which you do not want. Then you should find your geometry and literally just copy and paste these coordinates in, pressing enter each time. What I'm going to do is just put the Abaqus window somewhere where I can see this file. And you can see that now these points are beginning to construct an actual involute curve. And as I said, the spline interpolates these, so the more points you have, the closer it is to a true involute. When you're finished, press done. So here are our involute points, and we're expecting the addendum, so the maximum radius point, to be here. The next thing we'll do is create the root fillet geometry, and I can expand this window again now. So I will create arc, center and endpoints, clicking at the origin, and then just create a small arc and make sure that it's not snapping to anything, but it is on the dedendum diameter. And then we'll press escape to stop putting arcs in place. We will put a small line, and we will make it tangent to the involute. I don't know if you can see it, but you can create a tangent constraint just by it snapping in place. And then finally we will create an arc that connects those two, which is tangent to the dedendum arc at this point here. Now, we have a couple of things to fix before we try and impose any more constraints. So let's press add constraint, and I'm going to make a point of fixing that point there so it can't move, and I will also ensure that there is a tangent between this line and this arc. That is not what I wanted. Let's try that again. I will also fix the lowest radius point on the involute. You can now see why it is important to use these fixed constraints. There we are. Let's try that again. That is what I wanted. Now you can see that this is fully defined, and that is because I fixed this point here. So what I'm actually going to do is lift this fixed constraint, and I will press the delete button, select that constraint and press done. Now, with any luck, I can actually create, I can impose a dimension on this radius. So that fillet radius is currently 2, I'm going to make it 1.5. And now the root geometry moves such that that radius is 1.5. The next thing I will do is just create an arc, center and end points from the addendum point to the center, but I will do that such that it goes clockwise. Which it is not wanting to do. Let's try that again. There we are. And finally, I will mirror the involute. I'm going to click translate, but I'm going to long press it such that I can click mirror. And then I will select all the things I want to mirror. Now, the easiest thing to do here is just to draw a big box. Firstly, so I'm going to press copy, and I will pick the mirror line. And then I have to select the entities to mirror. So I'm going to draw a big box like this. And then I'm going to hold Control and deselect the things I don't want, which is these 3 lines. Everything else I do want to mirror, so all the red things are selected, and I'll press done, and then they get copied there. And that is our complete tooth part. Now, we defined the points on this involute such that when they were mirrored about the vertical line, they would create a tooth of the width that we wanted. So we don't have to worry about that. We'll press done again, and we get our tooth component. The next thing we'll do is create a material. We'll just right-click Materials and press Create. We'll call it Steel, and it will create mechanical properties, elastic, linear elastic isotropic with Young's modulus 207 gigapascals, and Poisson's ratio 0.3. Now, a little word about units. So far, all of the length dimensions that we have used have been in millimeters. The forces that we'll use will be torques in Newton millimeters, so the load dimension is newtons, and the length dimension is millimeters. Therefore, stresses, which have dimensions load per length squared, will be in newtons per millimeter squared, which is equal to megapascal. So 207 gigapascals is 2.07 times 10 to the 5 megapascals. That's what's going on there. The next thing we'll do is create sections, and we'll create a section which is solid homogeneous and call it tooth. And we will now go plane stress or plane strain thickness and give it 30 millimeters of thickness, and we will assign the material steel to that section. We'll do the same thing again, but this time we'll create a section and call it web. And this one will give a slightly thinner out of plane thickness, so 25. Now we can go back to parts, and we can actually go to tooth, right click section assignments, click create. We'll uncheck create set, and we'll hit the actual part itself to select it in red, and we'll press done. That section assignment, which is for this red picked region, will use the tooth section, and thickness assignment from section is what we want. We can do the same thing by expanding the web part. Right click section assignments, create, select the web, done, section assignment, web, done. Now we've told Abaqus that this tooth part and this web part are so thick and they're made of steel. We can now go down to assembly, and we'll press switch context, which would be a similar thing to just changing the context menu like this. We'll press create instance, and we'll create instances of the shaft through to the web. I just held control there, sorry, I held shift even to allow me to select all 3. And we will mesh on the actual parts rather than on each instance. I'll press OK. So this is what these 3 components look like assembled. We've got the shaft, and then the web, and then the tooth. These are going to be the upper cam, so I will translate them to start with by the distance between the 2 centers of the 2 cams. What I'll do is click translate and select all 3 of these instances, and then I will translate them upwards from the origin, that's the start point, and the end point will be at 75.2 millimeters above. I pressed the wrong number there, so let's try that again. We've now decided that that position is OK, so we press OK. And we'll press X, so we don't have to translate anything else. We'll now press rotate, and we will select these instances to rotate, but we will choose the center of rotation to be that reference point there. Then we'll rotate them by negative, because I'm going to do a clockwise rotation, 157.6 degrees. This is the transform that you can calculate based on where you want your initial tooth positions to be. And we'll select away from that. Now we want another instance of those parts, so we'll click Create Instance once more, press Web, hold Shift, press Shaft, and press OK. And finally, we will rotate these instances so that they are in contact. So rotate these three about the origin and by an angle that is 7.5 clockwise, which means it's negative. That brings them into contact. Now, the next thing to do is create the two steps of the analysis. The first step we will call, the first step after the initial step I should say, because the initial step is required by Abaqus, we'll call torque. And this is the loading step. What it does is it ramps the torque up such that the contact can stabilize before any displacement happens. Contact is a non-linear problem, so we'll turn non-linear geometry on, that's what NLGeom means. And this will happen over time period 1. We will change the incrementation such that the initial increment size is very small, and the maximum increment size is as big as it needs to be. So this will allow our contact to gradually ramp up. And the time period arbitrarily is a single second. Next, we will create the displacement step, which is the gears rotating such that the contact actually moves along the surfaces. We will assign this a time period equal to the angle in degrees that we want the cams to rotate. So I'm going to call this 30 degrees, and on incrementation we're going to increment in 0.5 degree steps. Now you might ask why the time is controlling the angle of rotation. That's because I'm going to specify an angular velocity of 1 degree per second. So any time in this step is analogous directly to an angle of rotation in degrees. And I'll create a very small minimum increment just in case it requires smaller increments to stabilize. Everything else can be left at its defaults, and you notice nonlinear geometry has been propagated. Now we'll edit the field output request. Notice that it has two states in the torque step and the displacement step. Because displacement is propagated, currently it's the same as the torque step. So we'll just edit it like this. And what we'll do is we need stresses and we need displacements and we need contact stresses, but we don't need strains or forces. So we'll just uncheck those and press OK. Notice that now the displacement step says modified, so I'm going to edit that and it should actually be the same. What I'll do now is just create an interaction property. I'm going to do this before I create the interaction because we use the interaction property in a second. It's going to be a contact and we're going to call it hard frictionless. This contact property has normal and tangential behavior. So the tangential is frictionless and the normal is hard contact with default constraint enforcement, and we will allow separation after contact. That's all we need to do. We'll now right click interactions and press create. The interaction we're going to call contact because that is the interaction we want, and it will be a surface to surface contact. It will happen from the torque step onwards. Then we will select the master surface that we want. One way to do this is just to draw a box around the surfaces that we want to partake, and we will also choose a slave type surface. What I can do now is just draw a box around those surfaces and then deselect the things that we didn't want by holding Control and clicking. Done. I will keep the default setting so everything else in this dialog box, and notice that there is only one contact interaction, so hard frictionless is what we are using for this. I'll now go down to constraints. With constraints, we tie the shaft to the web and the web to the tooth. So there are 4 constraints to create. First one I'm going to call shaft web 1, and what I'll do is just hide every part that is not the shaft on that component. So if I press create display group, I can go to part/model instances, go to shaft 1 and press replace. Now that's the only thing we can see. If I dismiss that, I can then go back to say this is in fact a surface. I'm going to select that, I'll press done, and I'm going to select the magenta side, which is the side nearest the rest of the component. Then I'll press surface for the slave type, but now the web is hidden, so I'm going to go to web 1, press replace, dismiss, and click that surface. This just makes absolutely sure that we're definitely picking the right surfaces and we haven't picked the shaft twice, for instance. All the other options, their defaults are okay. We're going to do the same thing 3 more times, so bear with. Constraints, we'll create a new one, we'll call it web tooth 1. It'll be a tie constraint, we'll continue, we'll select surface, and then we'll now hide that web and show the tooth. There we are, surface, bam. 2 more to go. This will be shaft web 2. We'll go surface, and we'll show that shaft, which is this one. We'll select the magenta side again, because it is nearest to the rest of the gear, and once more we will show the web of that component. The final constraint will tie the web of the second one to the tooth of the second one, and we will select the appropriate surfaces as before. Very nearly there. As a general rule, you can hold Shift to add things to the selection and Control to remove things from the selection, just so you know. Now we need to add a load. So what we'll do is just show everything again by pressing create display group, and then we'll go all and we'll press replace. Dismiss. If we right click loads and press create, we can then apply a load which we're going to call torque, and this will be a moment, surprisingly. It'll happen in the torque step, surprisingly, and we'll press continue. We're now going to apply this torque to the lower cam's reference point. So I said that the shaft would actually be used for applying the torque, and this is how we do it. We apply it to the reference point. The magnitude of the torque, I'm going to use 100 Newton meters, which is to say 100,000 Newton millimeters clockwise, so negative because we look from the positive Z direction and anti-clockwise is positive. That's us. That's the only load we need. Everything else is a boundary condition, which we will create. Firstly, I'm just going to fix the reference points by creating a constant displacement of 0 at the reference point of the top one. Notice that I'm not fixing the rotational, just the translational degrees of freedom. And I will create another one which does exactly the same thing to the lower cam. Again, applying at the reference point rather than anywhere else. 0 displacement in both cases. Next, I'll create a boundary condition called lock, where I actually do specify the rotation on the upper cam, and this will prevent that from moving in the angular sense. And finally, I'll create a boundary condition called displacement, which actually rotates the upper one. And I'll apply that rotation again to the shaft reference point, such that it is 1 degree per second clockwise. That is negative 0.017453 radians per second anticlockwise.
two of those boundary conditions were mutually exclusive. The lock and the displacement boundary conditions actually prevented they fight with each other. The lock boundary condition prevents that top cam from moving angularly, and the displacement boundary condition forces it to move angularly. So we have to turn these on and off at different times. We'll right-click boundary conditions and select manager. Then we will prevent displacement from happening until it gets the displacement step, and we'll actually turn off the lock boundary condition at the displacement step. There we are, and we'll dismiss that. So now we find that the boundary conditions are compatible with each other. The fixed boundary conditions both happen at both times, and I should definitely have called that fixed 2, and it'll make me sad unless I change it. Finally, we're almost ready to run, but we need a mesh. So I'm going to change context to mesh, and now we have a little bit of work to do. So remember when I said we mesh on part? I'll just select the web part for now, and I'll press seed part and then choose a global seed size. So for instance, 1 would work quite well. I can then just press mesh part, and the part meshes like that. For the tooth part, we can do exactly the same thing. So we can seed the part, and maybe we'll choose 0.8, and we'll just press mesh part like that. Now this mesh is okay, but it's not great. What we could really do with is far more elements at the flank where we will have contact, such that the contact can actually stabilize and we can get realistic stresses. So what we're going to do is seed an individual edge, and we'll select all the edges that we want to be resolved well. What we'll do is select a much smaller size for those elements and press apply. We'll have to delete the mesh that we've got, but that's fine. Look how many more seeds there are there. Now, if we were to mesh the part at the moment, what we'd find is that the mesh was a bit dodgy. We have really quite abrupt change in the element size here and here, which is something that we can avoid, and we should avoid according to finite element theory if we can help it. So the way we do that is actually by creating a different type of seed on these edges, and we're going to what's called bias them. So we'll go to bias, we'll go single bias, and we'll have the small ones at the same size as the minimum, and the large ones at the same size as the maximum. And then what we're going to do is we're going to flip the bias on this edge here. So if I just select that edge there and press flip, we can make the smaller elements closer to the flank. We'll press apply. Okay, now I've made a tactical error in that I actually want this edge here to be seeded as the others, which means we seed such that the element size is 0.8. There we are. We also notice that this element is smaller than this one, so we can change the bias there as well if we so wish. That's better. It's worth just checking your mesh manually, because Abaqus will make your mesh basically whatever you ask it to do. That doesn't mean it's a good mesh or that it'll give you good results. But I'm happier with that. One final thing we can do is partition the mesh such that there are fewer really fine elements in the region that we don't really need them in. This makes our simulation faster. So if we press partition faces, and I know my mesh will be deleted, but that's okay, and we create a line, actually first we'll create an arc, we'll put the arc, the center of the arc at the origin, and the endpoints at the midpoints of these lines. And then finally we'll put a vertical line like this, and press done. This partitions the mesh, and we also can choose to seed these lines like this. What we'll do is we'll have no bias, and we'll seed them in the same way as the rest of the part. What that means is that now when we mesh the part, it forces the elements on those lines to be seeded in the same way as the others, and as a result we get the mesh concentrated in the region that we want. So this is slightly more efficient to run this model. Now,
one thing that you might want to notice is that different mesh density might result in different stiffness. So this tooth might actually not be entirely symmetrical in the stiffness that you get, but there are many finite element considerations to think about, which I'm not going to cover here. One option could be to choose a mesh a little bit more like this, which is symmetrical and slightly more heavily refined on the tooth flanks. But this would be more computationally expensive, so it's your choice. While I'm here, I should also point out that you need to change the element type from whatever it defaults to plane strain if it isn't plane strain already. So I'll show you how to do that. If you go mesh element type, then you have to select which portions you want the element type changed on, so we select the whole part, and we make sure that it is plane strain, and we use reduced integration. And in this mesh there are both quadrilateral and triangular elements, so we have settings for both the quadrilaterals and the triangle. Obviously the triangles can't use reduced integration, and the quadrilaterals can. There are many settings you can play around here, but I find the defaults work for me, and we press OK to that. I should also show you just how to use mesh controls. This allows us, similarly we have to select the regions to apply the controls to actually change the type of mesh. So we have options quadrilateral, quad dominated and triangular. If I just choose to apply the controls just to one side, just to show you the difference, I could choose triangles. I would have to delete the current mesh, and then I could remesh, and I would find that a mesh entirely made up of triangles has quite a few more elements. But a mesh entirely made up of quadrilaterals potentially has rather more skewed quadrilaterals, and as a result, a quad-dominated mesh is quite a good compromise. This is the mesh that the Python script uses with the quad-dominated. So this is our purely quadrilateral mesh, and this is our purely triangular one, just for purposes of illustration. We've meshed the web and we've meshed the tooth, so now we can go back to mesh and we can press assembly, and we can see that fortunately our meshing on one cam has translated to the mesh on the other as well, because we meshed on part. At this point we hope that our model is ready to run, so we'll create a job and press create, and we'll go through to parallelization and just ramp up the number of processes that we can use to 4, which is the maximum on the student license that we have, and we'll press OK. And now what we can do is right click and press submit. If we get no warnings, then we can have a short party while the analysis preprocessor runs, and while that is happening we can right click and go to monitor. Monitor shows us how the simulation is doing. The analysis preprocessor has completed successfully, which means we can have a slightly wilder party. This is an achievement, and at this stage we can look to see how the steps are getting on. Because we chose 4 processes, sometimes the steps come in groups of 4, so what we can see is that gradually this time increment is ramping up to 1. So that was the torque ramping from 0 to the maximum torque. And now we're getting increments of 0.5. So that is the top cam actually rotating, and the bottom cam will rotate with it as a result of the contact. We asked for 30 seconds, so the total time will eventually be 31, and the step time in the displacement step will be 30. While the simulation is running, you can also just check how the results are at the moment by right-clicking and going to results. And what you can do is press plot contours on deformed shape. So this is where our simulation is at the moment. This is von Mises stress, and we can see that contact is pretty good. We could do with more elements inside the contact. We're not going to get great stresses out of this, but it's a good start. If I reverse the steps, we can actually see that these cams were rotating, and this shows us how that displacement was being applied to the top cam. Finally, we want to output the results. So what we're going to do is just create a path that lies along the tooth flank such that we can actually ask it what the stresses were. So we'll go back, results,
We'll close the ODB and we'll try that again. There we go. Now we have all 30 seconds. And what we can do is use the display manager in a similar way to the way we did earlier, which is to say, let's get rid of some part instances. So we're actually going to get rid of the first component and the web and the shaft. We'll remove those just to leave us with this. And then we're going to try and extract the stresses down this flank. So we will right click paths and press create. Path 1 is fine. We'll say node list and then we'll go add before. And we will select the corner node on this. So it starts at node 10, but then it goes to node 233 and begins to decrease incrementally. We'll find the end of the path that we want. I think somewhere here is about right. And we'll find that that's node 108. So we might make the assumption that this decreases incrementally from 231 to 108. So we'll press done. And we'll just change this vector very slightly. So I'll delete 108, and then what I'll do is have a vector that steps from 233 to 108 in steps of -1, and press OK. Now if we do that, what we find is that the path that we actually achieved is pretty good, but it's missing some elements. So for instance, there's a node missing there. If we wanted to add that node, what we could do is just modify this vector such that it goes to 124, comma, 123 through 108, colon, -1. And that should now have fixed that for us. Ah, we forgot to work out what that node is. We're going to have to add it. Let's add it afterwards. It was node 9. So we'll cancel that. We'll delete this thing. And we'll add node 9 in between the two vectors that we spliced. Now we have that extra point, and it is in the right point in that sequence. It is possible that we're missing other points as well. Abaqus gives no guarantee that it actually will number the nodes on a surface contiguously. The numbering is done to minimize the bandwidth of the stiffness matrix, so who knows what's actually happening. Finally, we want to ask what the stresses are on that path. So we'll press create. We'll go path, continue. So this is create XY data from path. Now we'll choose the path that we created. We'll choose true distance for the x values, and we'll choose a step. So for instance, step 48, where the time was 24, and we'll press OK. We can also choose what variable or field output we ask for. So at the moment, we're going for stresses, which is S, and von Mises stress. But equally, we could have, for instance, maximal in-plane principal stress, which would look slightly different. Notice the range on the color bar has changed here. We'll stick with von Mises for now, and we'll press OK. When we do that, we can then press Save As, and we'll call it XY Data 1. And then we have to export this XY data. So what we're going to do is report XY, all XY data, because we've only got one at the moment, and then we will create a file that we want to export this to, and we can choose where to put it as well. So at the moment it's in c/temp, which is the working directory. We can call this file flank.dat, and we can say, actually I wanted to overwrite that file, a single table for all XY data, and change engineering to scientific, because it will make your life easier if you ever want to parse this file. Press OK. Oh, we have to select some XY data. There we are. Now if I open up c/temp, there it is, that flank.dat file, and I can open that with any text editor that I want and examine it. Now it is very irritatingly a space delimited file, which means it's quite difficult to import into Excel, and you have to do a little bit of jiggery pokery to read it in Python or MATLAB.
Nevertheless, it gives you, in millimeters, an x-coordinate, which is the true distance along that flank in the tangential direction if we start at the tooth tip and end at the tooth root, and then a value of stress in megapascals. So we can see most of these stresses are times 10 to the 0, but we have a little bit which is times 10 to the 2, so we're looking at hundreds of megapascals in that region, which is a representative maximum contact pressure under quite light loading. So that is how to extract data from a model that you have created and run. But we could have done all of that quite a lot more quickly. So let me show you how to do that. So what I'm going to do is ask you to, on your C drive, create a folder called Abaqus MTT. And in that folder, make sure you have gears from geometry and mttgear.python, and also geargeometry.csv, these three files. Your geargeometry.csv file looks like this, and it contains all the parameters that we need to create the model that just happened. Notice, for instance, the torque, which was 100 Newton meters or kilonewton millimeters. The center distance, which we put in, is there. The web and the face width, which is the tooth thickness, are also there. I've decided the web's going to be the same thickness as the tooth for this model, but equally I could just make it the same as the previous one. And some other parameters which are documented in the coursework handout. We also have the flank paths for the pinion and the wheel, as will happen when you do your gears, but we've only asked for one tooth on each. N is one for each. So this is actually the file that you'll have to create yourself, but it is the input file for this script, Gears from Geometry. It must be in a folder called C Abaqus MTT to work. Then you will go to Abaqus and you will press Run Script. You'll locate Gears from Geometry and you'll press Run. Now what happens is the script automatically generates a coarse mesh, and it automatically generates a more refined mesh. Then it automatically submits the model for running, and it saves the Abaqus database.cae as well, so you can actually reopen it in the future if you need to. I'm going to go back to model now, and I'm going to look at the jobs that have been created. There's CamDemo coarse mesh and CamDemo refined mesh, and currently neither of them are running. What I can do to change that is just change an option here which says run the refined mesh please. So I'll do that and rerun the script. It doesn't matter that the geometry has to be recreated, it's created in seconds anyway. Now we can do the same thing as before, and we can actually monitor, this was the previous job, but we can monitor the running one. So I'm going to right click and press monitor. Just in case you don't like this method of monitoring, you can also look for status updates down here in the message window. The same information, or rather the relevant information, is condensed into messages which come up once the steps have begun. So there's, as before, 1 second's worth of torque load step, and then 30 seconds worth of rotate step. When this is finished running, it will automatically export the data, and you'll see this happen as the stresses are brought up on the screen. The beauty of the script, of course, is that the data analysis can be done, the data extraction can be done automatically, which means that those paths on the tooth flank and their respective node numberings can be done automatically. And that is a big benefit because manually defining those paths can be quite laborious. At the moment, data is being extracted on the lower cam, which we're calling the pinion, and then the upper cam, which we will call the wheel, gets extracted after that. Both contact pressure, so C press, and maximum in-plane principal stress, absolute, are extracted, and the details of what those stresses actually mean are in your coursework handout, but you should note that there is no post-processing done on them by the script. They are exported as if you had done it manually. Now the data extraction is complete, we can actually open up the folder to which they were extracted, which is also Abaqus MTT.
the folder we created earlier. And you'll see there are now CSV files for this CamDemo Refined Mesh job. There are 4 CSV files for the pinion and 4 for the wheel. And to ask what actually is in them, we can look at the paths that were created. So if we go to results and we look at these paths, we've still got path 1, which will now have no meaning because in this ODB the node numberings are different. But if we click edit on one of the paths, we can see this is the wheel tooth root path, which would be here where we see the bending stress at the tooth root. And then we can also look at wheel tooth flank, which is here where we see the contact stress. And the same is true of the thing we're going to call the pinion. Now, the beauty of this is that not only is the data extraction easy to do on a single tooth, but we can also just add teeth to the gear with no penalty in terms of the time we have to spend creating the model. So I'm now going to create 5 teeth on both gears, and I will refine only from tooth 2, but I will refine the mesh for 3 different gears. Refine the mesh for 3 different teeth, I should say, sorry. I'll save that file, and I'll press run script once more. Now, we see that the model that's been created is actually 2 gears rather than just 2 cams. And so with this method, as long as you can define the flank path in Cartesian space of the pinion and the wheel, you can create a model that is arbitrarily meshed, that is arbitrarily sectored, so has an arbitrary number of teeth, and export the data wherever you like. While this is running, one thing that we can briefly do is just look at the output files from the previous task. I'm just going to look at max in-plane principal stress on the tooth flank. I'll open up this, and because it's a CSV file, I can open it natively in Excel. What I can then do is graph, just using a line plot, the contact pressure as a function of displacement along the tooth flank. So I'll just do that now. What we see is, and I haven't graphed all the steps, but as the steps advance, the contact, which we can actually see it in terms of its Hertzian stress, advances in the positive direction along the tangential flank. So we're actually just looking at the contact itself moving along that flank, where each series is a different step. The structure of this file is such that we have time across the top. So remember I said time directly translates to roll angle. So here we have 0 degrees of roll, here 0.5 degrees of roll, etc. And so each series on that graph we just had was time. And then in the vertical axis we have x. I should also say that because this is contact pressure, or C-press, it's actually defined by Abaqus not as a stress but as force per unit length. So you'd need to divide by the face width, which is 30 millimeters, to get a representative stress. If I just plot that again, we can see that the maximum values are of the region 12,000 force per unit lengths. So if we divide by 30, we get something in the region about 400 megapascals, which is what we expect. The same is true on the tooth root. So if we open up von Mises stress on the tooth root, and just graph the whole lot, what we can see is that these stresses evolve gradually over time. Now, if we just graph the whole lot, we actually get each series in this graph being a row, whereas what we want is each series in this graph being a column, so be aware of that. And if we just do a small number, we can now see, looking from minimum radius to maximum radius, what the bending stress in the tooth root looks like. So this first millimeter is the dead end mark, presumably, and then we get a large stress concentration at the root fillet, which tails off down the cantilever of the tooth.
I will leave you there, but thank you so much for watching, and if you have any more questions, do let me know by email. My email is dam216 delta alpha mike 216, or you can ask me in the tutorials. Cheers guys!